Hello everyone, Sahil here. Today we will learn about gradient boosted machines. Now this is a really powerful range of machine learning algorithms. You will notice that these algorithms they win many machine learning competitions all the time. You will see their names there. Also, in many search engines, these algorithms are used, and it is really remarkable that these algorithms often outperform many complex, many big machine learning algorithms which are so complicated, yet these algorithms are so simple to understand, they are so simple to implement. So, this will be really interesting. So, let's just jump right in. Now, before we get into boosting, let me just give you a brief introduction of ensemble models because boosting is one of them. Now, what are ensemble models? Ensemble models are basically a group of models working together. So, we have this team, this group of people working together. We call them a company, we call them an organization. Similarly, a group of machine learning models working together, we call them an ensemble models. Now you can have different hierarchy here. You can combine these people, you can combine these different machine learning models in different ways to achieve different results, obviously. Now, there are two ways to combine them. One is to combine them parallelly and average the results. The second is to combine them in a sequence and get the result at the end. Now these two different variations basically solves two different problems. Now to solve a high variance problem, let's say you have a high variance learner, a very strong learner, and you want to solve the high variance problem. What is high variance? Basically you have a lot of features but you have less number of training examples to learn from. Now when you have a lot of features, you just split by the features. You have these different weak learners now which have low variance because the number of features is reduced. Now you combine these parallelly and you get a better result. Bagging is what I just defined, and random forest is just one variation of it which you have studied earlier. Now, parallel ensemble, combining the machine learning models parallelly, basically solves the high variance problem. Now we have the opposite problem. We have a high bias problem now. So high bias basically means we have weak learner. We have a weak learner. So this is really important. You have to understand the definition of a weak learner. It cannot be anything random. It cannot be anything that just predicts anything. A weak learner is something better than flipping a coin, a little bit better than flipping a coin. It has to have some amount of knowledge. It has to have something to contribute. It is not very good at it. It is a weak learner, but it has to have some knowledge to contribute. This is what a weak learner means. Now, when we combine these weak learners in a sequence with a bit of sophistication, which we will discuss later, when we combine these weak learners in a sequence, we solve the high bias problem. We get better results. This is a sequential ensemble. Boosting is just one example of it, and add a boost, which means adaptive boosting, is just one variation of it, which we will learn about later. We will learn about a whole range of different boosting algorithms. Now, another way to understand this is one analogy from electricity. Remember when we have different resistors and these different resistors have different resistances. Now, if you combine them parallelly, the final resistance is actually really low. It reduces the resistance, it reduces the variance. But if you combine these resistors in a series, it just adds up, it just increases the resistance. So it basically increases the variance. You can compare variance and resistance, and it is a good analogy to understand this because in a sequence it basically adds up the variance of different weak learners, and we have high variance, we have better variance, we had low variance earlier, we had high bias earlier. So now that you understand the hierarchy of these models, let us get into the intuition of boosting in particular now. Now let me just explain you the intuition behind gradient boosted machines, and it is really simple to understand. It is really intuitive. So we have these different high bias learners, these different weak learners, and we are trying to combine them in a sequence to get the best result, to get the correct result. So we start with a weak learner and we ask it to give us a prediction. Now when we get this prediction, because we have the right prediction, we can see that it is not the right answer. But just look at that prediction. It is not the correct prediction, it is not the correct answer, but it is not exactly wrong. If we take a small input of that, if we take a small contribution from that and go in that direction, we will actually reach closer. We will reach closer to the right prediction. So we are not taking that prediction totally, but we are just taking a small portion of it because it is improving our condition. So something is better than nothing. We are taking a small contribution out of that. Now this is the first step. The second step is that we will ask other weak learners and we will say that okay, all of you just give us your inputs and we will see which one performs the best. And because these are weak learners, we will take the one which gives us the best prediction. But of course, no prediction is right here because all of these are weak learners. So we will not take the whole prediction. We will just take a small contribution out of that. So we will ask all of these other weak learners and we will see that which weak learner gives us the best prediction so far, and we will take a small contribution of that again. So we are taking the direction here and we repeat it until we don't go closer to our right prediction. That is, we have exhausted all our weak learners. So this is the procedure. Basically, we are asking every weak learner and we are taking a small portion of them and we combine them to reach the actual prediction. So gradient boosting machines. This algorithm has different styles, has different variations. So we have these different types and they have their own idiosyncrasies because they have their different specific goals. We have these different specific targets and we introduce these slight variations in the same algorithm to achieve those goals. But at the core, the idea is the same. You are combining these weak learners into a sequence to get the best result. So let me just introduce the types here. So the first one is the adaptive boosting. So as was written in the earlier slide, that you take this weak learner, you predict. Now because you know the right answers, you take the misclassified ones and then you take the misclassified ones and give it to the other weak learners and get the best results. So this is a slight variation. You are taking the misclassified examples. This is adaptive boosting. You are adapting according to your mistakes. The other one is gradient boosting. It is really powerful. It is the most powerful, and we will talk about it later. XGBoost is an advanced version of gradient boosting. We will talk about it later as well, along with other versions. See, gradient boosting can be used for both classification and regression. You might be thinking that we are taking these little steps to reach our goal. We are taking the direction and we are taking these little steps. It basically looks a bit like gradient descent. You are minimizing the cost function, you have the direction, you only take a step equal to the learning rate, and then you do it again and again and again until you reach the global optimum. In fact, it is actually gradient descent, but in feature space. That's why it is so powerful. This is what makes it so powerful, and it actually gives you really good results. So the steps of this algorithm, you take a weak high bias learner, you get the predictions and you compare it with the real answers. This is the first step. Then you do the second step. You get a new weak learner, you get the predictions, compare it with the real answers and do it for all the weak learners and get the best ones where the difference is the lowest. You take this new weak learner, this is the new weak learner that you will add to your sequence, and you keep on doing it until the predictions and the actuals, the difference between these two doesn't decrease anymore. So let me just show you an implementation, a simple implementation of this algorithm which will give you much more clarity. So we start by getting the data. We are using the pandas library. It is used for playing with tabular data. So we have these Excel files, these CSV files, and we convert it into a data frame, and it just really helps us do the necessary things we need to do. The pandas library is kind of the standard in machine learning, and you should know how to use that. So we have the learning rate equals to 1 here. I will talk about it later. So we have this data frame, and I am showing you the data frame's head, the topmost part of the data frame. So what we have to do is that the age is our feature, and we have to predict the price using the age. So the price is our label. Let's say that your learner, your weak learner, your high bias learner decides that we will have different predictions for people below the age of 50 and above the age of 50. So we take the prices of people below the age of 50, and we take a mean of that, and we do the same for people who are elder than age 50, and these are our predictions. And we take these predictions and we subtract it from the real answers. When you compare these differences, you will see that when we have the people whose age is above 50, the answer is not that far away from the real answer. The difference is not that large. So this weak learner, this high bias learner, who doesn't have all the knowledge to solve this problem, is pretty good at that portion. It has the knowledge to predict for the people whose age is above 50. So this is our first step. Now we will start our second step. Now we take the second step. We get a new weak learner, and this new weak learner basically decides a new threshold, that for the people below the age of 50, we will have a new threshold which is age of 30, and we will decide people who are below the age of 30 and above the age of 30 differently. And it does the same thing, it takes the mean, and this is our new prediction. And we do the exact same step, and we subtract the predictions from the actual ones, and you will see that the difference is not that large. So we combine these two weak learners to get the better results. You can see that we combine the prediction from the second weak learner and we multiply it with the learning rate. We only take a small portion of that prediction. However, it was the whole portion this time, but this is not usually the case. So we combine these two weak learners in a sequence. You can see that the differences here, the differences between the predictions and the actual answers, they are minimized. They are not that large. You might think that these two weak learners, they don't really know about this problem. I mean, they don't have a lot of knowledge, and you might feel that we need a really big model to solve this problem. But still, you can see this is the magic of gradient boosted machines. The results that they are producing, they are pretty good. So let's just get to the main idea now. So XGBoost, it is one of the most popular gradient boosting machine algorithms. And before I explain you what XGBoost is, it is basically extreme gradient boosting. XG means extreme gradient boosting. Now what gradient boosting is that? It is different from adaptive boosting. So where is the difference? The difference is how you select the new weak learners. How do you add the new weak learners so as to form a sequence? So in adaptive boosting, we were looking at the misclassified examples. That was adaptive boosting. Now in gradient boosting, this is not the case. We are adding new weak learners to improve the performance, but the criteria to add these new weak learners is different. What is that criteria? So in gradient boosting, the new weak learner is added on the fact that it has to reduce the loss function. So we have a weak learner, we compute the loss using the loss function. Now this new weak learner which is added in the sequence, it will be added in this sequence only if it reduces this loss. So it has to add some improvement. This is the basis, this is the basic concept behind gradient boosting. Now what is extreme gradient boosting? Now extreme gradient boosting, XGBoost, is just an advanced version of gradient boosting. So at the core, the concept is the same. Now, what is the advantage? The advantage is that it is faster and it is good at computation. So its efficiency at computation is pretty good. It's better than gradient boosting. It is faster than gradient boosting. But at the core, the concept is the same. We also have some alternatives to XGBoost, like Light GBM or CAD Boost. We will talk about these later. These are remarkably similar. They have their own different styles, these different idiosyncrasies which sets them apart, and they have their own merits and demerits, and we will talk about them later as well. So let's start implementing XGBoost now. You will see how easy it is to implement XGBoost, yet it is so powerful. So we start with importing the necessary libraries. So when we write import numpy as np, we are basically saying that import the numpy library but use it with the name np. The numpy library is used for mathematical operations, primarily matrix multiplications. The pandas library I already told you, it is used for tabular data. The matplotlib library is used for plotting different kinds of charts, different kinds of graphs, and it helps you visualize different kinds of things. Now we are importing the XGBoost package as XGB. After that, we get the data. Now this data set we have already used earlier. It is the California housing data set. We have these different features and we have to predict the target. Now that we have imported all the necessary libraries we need and we have the data now, I will talk about the hyperparameters that you need to tune so that you can get the best results, because these are really important. After that, we will talk about how you can use them and we will implement them and you will see how we get the results as well. So let me just explain you the impacts and the relations of these different hyperparameters that XGBoost has. These are really important and these will directly impact the results, the performance of your algorithm. So let me just explain you one by one. So the max depth hyperparameter. What does it mean? The max depth hyperparameter basically defines the complexity of the weak learner you have. So as I told you earlier that you have this weak learner. It is a high bias learner. It doesn't have the capability to learn a lot of patterns. But if you will increase the value of max depth, it will learn a lot of patterns. Now we don't want that because it will push your algorithm towards overfitting, which you don't want. The second one is the number of estimators. The number of estimators basically defines the number of weak learners you have. So if you will have too many weak learners, it will also push your algorithm towards overfitting. So there is a trade-off here. You don't have to use grid search to determine the right value of the hyperparameters. It will take too much time, it will take too much computation on your part, and it is just not productive. You have to use these relations. So you can see on the right side that the max depth and the number of estimators. These two hyperparameters push your algorithm towards overfitting. But we can balance that. We can balance that using these other four hyperparameters, which is the subsample, the learning rate, the call sample by tree, and the minimum child weight. These four hyperparameters push your algorithm towards underfitting. There has to be a balance here to get the best results. So the third hyperparameter, the learning rate, which is self-explanatory, you have to use the shrinkage factor. Now these three hyperparameters, the learning rate, the minimum child weight, and the objective. The objective is self-explanatory, it is the objective function. These three hyperparameters are similar to random forest. So what you learned about them in the random forest video, the same things apply here. Now we have these two hyperparameters which are left, the subsample and the call sample by tree. These two are actually similar. When we are using subsample, we are talking about the training examples. And when we are talking about call sample by tree, we are talking about the columns. We are talking about the features. Now, both of these hyperparameters basically take a fraction. So in subsample, we take a fraction of the training examples. In cold sample, we take a fraction of the features, the number of features. Now, if you will take a small fraction of the number of features, it will push your algorithm towards underfitting. That's why it pushes your algorithm towards underfitting. These four hyperparameters, they push your algorithm towards underfitting. So there is a trade-off there, and you can use these trade-off to get the right value. And this will actually impact your algorithm. You have to tune these hyperparameters to get the best results. So let's just start implementing XGBoost now. So now let's start. We have the hyperparameters now. So we start with initializing them. The max depth, the objective, the learning rate, the subsample, the number of estimators. Now you know what these actually mean and what are their effects on our algorithm. After that, we initialize our model. Because this is a regression problem, we take the XGB regressor and we give it the hyperparameters that we are using. After that, you just have to give your training set, that is your X train, your features, your Y train, your labels. The training features, the training labels, and you call the dot fit function and it basically fits your model. Now you can use this to predict. You can use this model to predict. You can just call model.predict and you give it the test part, which is the test set, and you get the predictions. And after that, you can just use these predictions to compare with the testing labels to get the error. That is what we do in the next step. We use the RMSE function. RMSE means root mean squared error. It computes the root mean squared error. We give it the predictions and the testing labels. And you can see that we are getting like 0.54 here. This is not really good, but this is not bad as well. It is better than a lot of algorithms. It is not bad performance. So we will get even better performance in the next slide where we do the needed hyperparameter tuning. So to get better performance, you have to be aware that XGB as an algorithm is prone to overfitting. So you have to be careful about that. So let's just do the hyperparameter tuning. What we are doing here is that we are splitting the training set into training and validation set. We will use the validation set to get the right hyperparameters. So we get the eval set, which is basically the segregated training set and the validation set. Now we use it to train again. You can notice that the number of estimators has been increased. It was 100 before. So we are trying to get more number of weak learners. Basically, we are pushing it towards overfitting. We are trying to get more performance out of that. So we use the same code and we code it. You can see that the error has reduced now. So it is giving us better performance now. And this is actually pretty good. This is pretty good performance. So just like other boosting algorithms, people tend to think that these algorithms are black box methods. We don't really know what is happening inside them. We don't really have the intuition whether these algorithms really know what is the right decision process. So there are different methods to account for the feature importance. Which features are the most important? Which features are used for the decision process? There are two scoring methods to do this. The first one is the frequency method, the second one is the gain method. The gain method is probably better, but you can use both of these methods. And you will see this chart that it plots, and you can get the information that which features are actually contributing to the decision process, and this is really useful information. And you can also use it while doing the hyperparameter tuning and to basically understand what the algorithm is actually doing, whether it knows or not what is the right decision process. So as I told you earlier that we also have some different variations of XGBoost and they have their own merits and demerits. So we have Light GBM and CAD Boost. So you can see that there is no special splitting technique when it comes to XGBoost. But Light GBM and CAD Boost, they have their own specific splitting technique. Also the leaf growth in CAD Boost, which is when we are talking about trees, it is balanced and it makes it less prone to overfitting. In XGBoost and Light GM, that is not the case. So what is the advantage? What are the merits and demerits? So you can see that the Light GBM is the fastest. It is the fastest to train, but when it comes to accuracy, the CAD boost is the best. The accuracy of Light GBM and XGBoost are almost similar. In some cases, Light GBM is better. In some cases, XGBoost is better. But yeah, when it comes to speed, Light GBM is the best. Like any other machine learning algorithm, gradient boosted machines also have their own pros and cons. Now, these are really capable, these are really powerful algorithms. They can be applied to a wide range of problems and they can still learn the complexity of the problem and they can give you really good results. But they have their own demerits too. When you start to train them, you see that they are actually really slow to train. You have to tune a lot of hyperparameters. And again, I am telling you that don't use grid search to tune the hyperparameters. You have to tune the hyperparameters yourself. Otherwise, you will waste a lot of time and computational resources. Now, tuning the hyperparameters yourself, it is a lot of work, I understand. This is one demerit of gradient boosted machines. Also, when you have these different weak learners in a sequence working together and giving you really good results, it is difficult to understand how are they giving you the results. You can get the features, you can see which features are responsible for the decision making process, but still to understand how the algorithm is making this decision, it is really difficult to understand that. It is really difficult to get the insights as to how the decision making process is working. So these were some pros and cons of gradient boosted machines. And again, these are really powerful, really interesting algorithms.